Hey everyone, let's jump right into this explainer and absolutely crack the code on how nonmetal atoms build some of the most crucial structures in our entire universe. Welcome to our deep dive into the fascinating world of covalent bonding. So, you probably already know that ionic bonds work by just, well, transferring electrons from metals to nonmetals. Easy, right? But here's where we run into a really fascinating microscopic problem. What actually happens when two nonmetals interact? I mean, if both of them desperately need an extra electron to finish up their outer shell, giving one away just leaves one atom worse off. It's a total stalemate. So, how exactly do they solve this microscopic standoff? To solve this atomic puzzle, here's our roadmap for today. First, we'll look at the covalent bonding solution, then visualizing simple molecules, followed by strong bonds versus weak forces, and finally, we'll check out some real-world molecular properties. All right, section 1, the covalent bonding solution, or the cooperative fix for nonmetals. Let's see exactly how these atoms negotiate their need for a full outer shell. You see, instead of outright theft or a one-way transfer, nonmetals do something pretty clever. They compromise. A covalent bond forms when pairs of electrons are actually shared between nonmetal atoms. By sharing these outermost electrons, both atoms get to achieve that super stable noble gas electronic configuration they're basically striving for. It's literally a cooperative fix. This brilliantly illustrates the concept in action. Take a look at these two chlorine atoms. Now, each one has 7 electrons in its outer shell, which means they each need just one more to hit that magic number of 8. So what do? They overlap their electron shells and share a single pair. By doing this, both atoms essentially get to count those shared electrons as their own. It instantly satisfies both atoms. Boom, forming a single covalent bond. Moving right along, section 2, visualizing simple molecules, translating the microscopic. Now, what's really cool is how we actually translate these totally abstract microscopic interactions onto a piece of paper. Drawing a dot and cross diagram is highly logical if you just follow a few steps. Step 1, just draw the outermost shells. Step 2, you overlap them right where the bonding happens. And step 3, fill the overlapped area with those shared electron pairs. We use dots for one atom's electrons and crosses for the other. Why? Because it makes it perfectly clear where each electron actually came from. Oh, and just a quick classic examiner tip here. Always ensure those shells end up full. And keep in mind, the first energy level only holds 2 electrons, while the second energy level maxes out at 8. Here we can clearly see the progression from those detailed dot and cross diagrams to something, well, a little bit simpler. Take a look at water and methane. Now, while the dot and cross diagrams are great because they show exactly where every single electron comes from, let's be honest, they can get pretty messy for larger structures. So we simplify things into what's called a displayed formula. In those formulas, a single straight line simply represents one shared pair of electrons. Honestly, it's just a much faster way to draw these simple molecular substances. Let's kick it up a notch with a slightly harder example and see how this built. Check out ammonia, NH3. So nitrogen is in its second energy level and has 5 outer electrons, right? Meaning it needs 3 more to reach a full 8. So what does it do? It smartly pairs up with 3 separate hydrogen atoms. Each hydrogen shares its single electron to get a full outer shell of 2, and in return, the nitrogen gets the 3 extra it needs from those hydrogens. It's a really perfect illustration of how multiple single covalent bonds can form all around one central atom. Okay, moving into section 3, strong bonds, weak forces, also known as the examiner's trap. Now guys, pay super close attention here because we are officially entering dangerous territory. This is a classic examiner trap. You absolutely must understand the massive difference between forces inside a molecule and forces between molecules. You've got to remember that intramolecular covalent bonds, those are the shared electrons holding the atoms together inside the molecule, those are incredibly strong, like super strong. However, the intermolecular forces acting between separate neighboring molecules, those are actually very weak. Please do not mix these two up. When you melt or boil a simple molecular substance, you are only breaking those weak intermolecular forces. You are not breaking the strong covalent bonds themselves. And that brings us to section 4, real-world molecular properties, from micro to macro. Let's look at how these tiny microscopic quirks actually dictate the physical properties of our everyday world. Because those intermolecular forces we just talked about are so easily broken, simple molecular substances boil and melt at really low temperatures.
This is exactly why things like chlorine, ammonia, and methane are usually just gases or liquids sitting at room temperature. Furthermore, because all the outer electrons are securely locked up in those shared bonds, they completely lack any free ions or delocalized electrons to carry an electrical charge. And that leads us to another really important real-world property, poor electrical conductivity.
And this brilliantly illustrates why that lack of conductivity actually matters to us in our daily lives. Just think about household electrical wiring. That lack of free electrons in covalent molecules, it's exactly why the plastic coating around these wires makes for such a perfect insulator. The covalent compounds in the plastic simply do not allow a flow of charge. It keeps the electrical current safely inside the conducting wire, which, protects all of us from getting nasty, dangerous electric shocks. As we wrap up this explainer, I want to leave you with a really fascinating thought. We've seen how these small, microscopic sharing agreements create simple molecules that form, frankly, pretty weak liquids and gases. But it really leaves you wondering. If simple molecules are so easily pulled apart, what kind of immense, mind-bending physical properties emerge when billions or even trillions of atoms share electrons, locking together to form an endless 3D giant covalent lattice? Like a diamond? Well, we're going to have to leave that indestructible superstructure for another time. Thanks so much for joining me on this explainer, and keep questioning how the microscopic shapes our massive world.